Well, let's continue talking about different sets of postulates here. The first big set of postulates for Euclidean geometry was, of course, Euclid's set of postulates, which are very quickly right there. But as time went on, people found that there were certain things that Euclid was really probably assuming that he didn't quite make explicit. So different people came along to try to make Euclidean geometry, more rigorous. And eventually we get to David Hilbert, who was a mathematician from the late 19th and early 20th century, and he was probably considered the greatest mathematician of his time, certainly one of the greatest anyway, and he did lots of things. He worked in lots of different areas of mathematics, but one of them he worked in was geometry. And these are the set of postulates that he came up with, and ever since they have been put forward in the early part of the 20th century, these have kind of become the standard ones for lots of people's treatments of geometry. So he had several undefined terms. Points, lines, plane were undefined. He called lie on, contains, between, and congruent also were undefined terms. And then he had axioms that were placed in different groups: axioms of incidence, axioms of order, axioms of congruence, axioms of parallel, and in continuity. So let's just kind of quickly run through what each one of those are. Postulate, incidence postulate 1. For every 2 points A and B, there exists a line that contains each of the points A and B. This assumes those 2 points are actually 2 distinct points. Postulate 2, incidence 2. For every 2 points A and B, there exists no more than one line that contains each of the 2 points. Okay, so when it says there exists a line, that means at least one line that contains each set of points. That would be postulate 1 and 2. Now, he could have combined 1 and 2 and said, for every 2 distinct points A and B, there exists exactly one line that contains each of the 2 points. But he split each part of that statement up into postulate 1 and 2. Postulate I3, there exist at least 2 points on a line, and there exist at least 3 points that do not lie on a line. So there's actually 2 statements there. So that's an existence axiom. So the first part, there exist at least 2 points on a line, says if there's a line, then there exist at least 2 points that are on that line. And that's an if-then statement. The second part is actually an existence statement. There exist at least 3 points that do not lie on a line. So there a set of 3 non-collinear points does exist. Postulate I4 says for any 3 points A, B, and C that do not lie on the same line, there exists a plane alpha that contains each of the points A, B, and C. For every plane, there exists a point which it contains. So, if we put that in if-then form, the first one, I4 says, the first sentence says, if A, B, and C are 3 distinct points that do not lie on the same line, so it's a non-collinear set of 3 points, then there has to exist a plane that contains A, B, and C. And then part 2 says, for every plane there exists a point which it contains, says if P is a plane, then there exists a point X in that plane. So notice the first part, you start with the 3 points and you determine there has to be a plane. The second sentence says you start with the plane and determine there's at least one point in it. Postulate I5 says for any 3 points A, B, and C that do not lie on one and the same line, there exists no more than one plane that contains each of the 3 points, A, B, and C. So that's kind of like the first part of I4. The I4, it says there exists a plane. That means at least one plane containing 3 points. And this says no more than one plane. So again, those two could have been combined and said there exists exactly one plane that contains the 3 points. Postulate I6, if 2 points A and B of a line A, line plane alpha, then every point of A lies in plane alpha. So if 2 points are on a line, then the entire line, if 2 points on a line lie in a plane, then every point of the line has to be in the plane. So I7, if 2 planes, alpha and beta, have a point A in common, then they have at least one more point B in common. Okay, and postulate I8, there exist at least 4 points which do not lie in a plane. So the postulate set that we're going to use is very much uses postulates, some of these almost exactly, or are equivalent versions of these things up here on some of them. Then you have some axioms of order. Okay, and so order axiom 1, if point B lies between point A and point C, then points A, B, and C are 3 distinct points of a line, and then B also lies between C and A. Postulate 2 on the order, if 2 points A and C, for any 2 points A and C, there always exists at least one point B on the line AC such that C lies between A and B. Postulate order 3, of any 3 points on a line, there exists no more than one that lies between the other 2. And number 4, let A, B, and C be 3 points that do not lie on a line, and let A be a line in the plane containing A, B, and C, which does not meet any of the points A, B, and C. If the line A passes through a point of the segment AB, it also passes through a point of the segment AC or through a point of segment BC. So we'll have something similar to postulate 4 eventually. The order postulates 1, 2, and 3, we're actually going to prove those as theorems because we're going to have we're going to be able to define some of betweenness in terms of a distance metric that we're going to introduce. So we're going to do things a little bit differently than Hilbert at that point. We have some axioms of congruence. The first congruence axiom, if A and B are 2 points on the line A, and A prime is a point on the same or another line A prime, it is always possible to find a point B prime on a given side of the line A prime such that the line segment AB and the line segment A prime B prime are congruent. Number 2, if a segment A prime B prime and a segment A double prime B double prime are congruent to the same segment AB, then the segments A prime B prime and A double prime B prime are congruent. So essentially congruence of line segments is transitive there. On a line A, let line segment AB and BC be 2 segments which, except for B, have no points in common. Furthermore, on the same line or another line A prime, let A prime B double prime and B prime C prime be 2 segments which, except for B, have no points in common. In that case, if line segment AB is congruent to A prime B prime and BC is congruent to B prime C prime, then AC is congruent to A prime C prime. And next, if angle ABC is an angle and if BC is a ray, then there's exactly one ray, B prime A prime, on each side of line B prime C prime such that the angle A prime B prime C prime is congruent to angle ABC. Furthermore, every angle is congruent to itself. And then we have the side angle side postulate. If 2 triangles, triangle ABC and triangle A prime B prime C prime, the congruence is segment AB is congruent to segment A prime B prime. AC segment is congruent to segment A prime C prime, and angle BAC is congruent to angle B prime A prime C prime are valid. Then the triangles, then the other angle ABC is congruent to A prime B prime C prime is also satisfied. Then you've got an axiom of parallels. This is a parallel postulate. Let A be any line in A and capital A a point that's not on it. Then there's at most one line in the plane that contains line A and point A and passes through A and does not intersect line A. So there's a unique parallel. So that is that sort of replaces Euclid's fifth postulate. And then you have a couple of things about continuity here, and these basically are equivalent to giving us some of the properties of real numbers. First is the Archimedes axiom. If segment AB and segment CD are any line segments, then there exists a natural number n such that n copies of CD constructed contiguously from A along ray AB will pass beyond the point B. So in other words, you can extend a line as far out as you need to. That's basically the same as Euclid's 2, postulate 2. And line completeness, an extension of a set of points on a line with its order and congruence relations that would preserve the relations existing among the original elements as well as fundamental properties of line and order congruence is impossible. So I'm not going to go over exactly what each one of those mean, but those are the postulates the way that Hilbert set them up. And we'll have some similar kind of postulates in the version that we're going to do, although we're going to do things a little bit differently in my notes, and we'll introduce those as we go along.